Welcome back to the Deep Dive, where we take complex research, strip away the jargon, and really try to extract the most essential, actionable knowledge that you need.
And today we're diving into the heart of a real technological paradox, the large language model.
It's the new reality, isn't it? Whether you're a developer, an analyst, or, just intensely curious about this stuff, you are probably relying on LLMs for code generation, for summarization.
For incredible boosts in productivity. I mean, they're everywhere. But that reliance, it introduces a new and very sophisticated security fault line.
That fault line is the entire focus of our deep dive today. We're looking at what happens when that perfectly generated block of code, the one,
Yeah.
it includes a dependency, a package name that is completely fake.
Completely fake, yet it looks totally plausible.
Exactly. And worse, what if that fictitious name isn't just a random error, but a high-value target just sitting there waiting for a malicious actor to register it and, well, launch a massive software supply chain attack?
That is the nightmare scenario we are here to quantify today. Our analysis is built around several key sources, but particularly this fascinating paper titled, "We Have a Package for You."
Right.
And our mission is really to explore how the very sophistication that makes these advanced LLMs excellent coding partners, their mastery of instruction following, their linguistic structure.
How that also makes them exceptionally powerful and economically cheap tools for compromising the open source software supply chain.
It's a classic dual-use problem.
The core of the problem, you said it, it lies in these dual-use capabilities.
Yeah.
Instruction-following LLMs have improved so dramatically that they've really amplified existing security risks.
For sure. They make standard computer security attacks. They make them so much easier to deploy. Everything from large-scale scams to sophisticated infrastructure compromise becomes frighteningly easy.
And critically economically viable for bad actors.
That's the key.
Yeah.
The economics have shifted.
Okay, let's unpack this and start with the foundation. Before we even get to the actual fake packages, we need to understand the fundamental shift that makes LLMs, especially the highly tuned instruction-following models, vulnerable to traditional cybersecurity attacks.
Right.
And here's where it gets really, really interesting. Researchers noticed that these models, they behave remarkably like standard computer programs.
Which means they can be exploited like them.
Exactly.
It's a profound observation. When an LLM is instruction following, it's not just, generating fluent text. It's exhibiting what the researchers are calling programmatic capabilities or gadgets.
Gadgets, I like that term.
It's basically computation emulation. We often forget that what an LLM does internally, the token generation, the attention mechanism, it's a complex sequential computation. It's all based on weighted probabilities.
And if it's performing computation, it has to have computational building blocks. So what are those foundational gadgets that enable these classical security attacks?
We can pretty much identify 4 primary capabilities, and they're analogous to foundational computer science structures. The first one is string concatenation.
Okay, joining strings together.
Yep. The ability to logically join separate pieces of text or, tokens to form a single coherent output or command.
That seems innocuous enough on its own, but in security, that's the definition of assembly, isn't it?
It is. It absolutely is. The second capability is variable assignment. This is where the model can hold an instruction or string and refer back to it using a placeholder, even if that placeholder is only implicitly defined.
So like defining A and B and then telling the model to do something with A plus B.
Precisely. The third capability is sequential composition, which is really just the ability to follow a precise sequence of instructions, processing them in order. It's a necessary condition for any successful multi-step task.
And the final one, this really brings us into real programming territory. Branching.
Exactly. Branching, or if-then logic, allows the model to make conditional decisions based on the content it receives. For example, if the input meets criteria X, output Y, otherwise output Z.
So concatenation, assignment, sequential composition, and branching.
Those 4 capabilities give LLMs the ability to emulate really complex multi-stage computation.
You mentioned this is analogous to classical security attacks. The sources drew a really clear line to something called return-oriented programming, or ROP. Can you elaborate on that connection for us?
Yeah, that analogy is absolutely crucial for understanding the threat model here. In traditional ROP, an attacker doesn't inject entirely new malicious code.
Yeah.
Instead, they hijack the flow of control and they chain together existing tiny fragments of machine code. These are the gadgets that are already present in the legitimate program's memory.
So they're using the program's own building blocks against it.
Perfectly put. By chaining these benign fragments, the attacker can force the program to execute a malicious function. In the LLM context, the attacker is chaining the model's own pre-existing benign capabilities, its ability to concatenate strings, its ability to follow sequences, to execute a final malicious command that would otherwise be filtered out.
So if the model acts like a vulnerable program, it can be exploited like one. And the primary goal for any malicious actor trying to weaponize an LLM is, of course, bypassing the built-in defenses,
The input and output filters.
the ones used by the major API providers like OpenAI.
That's the choke point. Those filters are designed to prevent the generation of content that's deemed harmful, hate speech, specific types of scams, phishing emails, that sort of thing.
Yet the researchers found that attacks inspired by this traditional computer security approach,
Yeah.
they achieved up to a
100% success rate.
100% in early controlled tests. That's astounding.
It really is. It shows the fundamental nature of the vulnerability.
Let's break down how they did that. We got three main vectors. The first one is maybe the most straightforward application of this classical defense evasion, obfuscation.
Right, obfuscation. It involves changing the attack payload just enough to avoid pattern detection, but not so much that the target system, in this case the LLM, can't decode the intent.
So for an LLM, this just means slightly changing the text prompt to get around the keyword filter.
Exactly. The sources gave the example of changing COVID-19 to CVID or Elders of Zion to Elders of Zion.
And the irony here is just fascinating to me. The model's greatest strength, its ability to infer and correct meaning, is being weaponized against its own security filters.
It's the ultimate dual-use problem, isn't it? The models are so good at instruction following and error correction that they'll often fix the deliberate typo in the input.
And in doing so,
They produce a high-quality, fully corrected, and therefore more convincing malicious output, even though the input was garbled precisely to deceive that filter.
okay, so moving beyond just simple text changes, the second attack vector is more structural. It leverages those gadgets we were just talking about.
Code injection or payload splitting.
Payload splitting.
This is a direct application of that ROP analogy. The attacker breaks the malicious instruction into multiple non-triggering parts. So imagine a command that says, generate a script to steal credentials.
Okay, that's definitely getting blocked.
For sure. But if they define string A as generate a script and string B as to steal credentials, both of which are individually benign.
And then you just instruct the LLM to concatenate and execute the combined string.
You got it. It's just like the smart GPT example mentioned in the sources. They fed the parts of the attack in as variables, set up this fictitious model name, and then just asked the LLM to run the final concatenation.
So the input-output filter, it only sees these harmless variables being defined and some simple requests.
Nothing that would trigger a security alert, but the LLM's inherent programmatic capability executes the assembly, creates the final harmful command in its own sort of internal process memory.
Which it then executes and outputs.
And this technique is incredibly effective because it just sails past any static analysis of the input prompt.
And the third, and maybe the most complex, vector is virtualization. This sounds like creating a whole fake universe for the LLM to operate in.
That's a great way to put it. It is. This attack vector involves encoding the dangerous instructions inside a fictitious scenario.
Yeah.
You're effectively creating a virtual machine context within the model session.
It's a staged attack then. It requires multi-step prompting.
Yes.
Can you walk us through that staging process? Because this seems key to understanding how sophisticated human engineering can just defeat these automated filters.
It's essentially world building, but with an insidious intent. The attacker uses a series of prompts to boot the LLM into a specific trusted or, fictional state. For example, they might spend the first 3 or 4 prompts establishing the character, the history, and the personality of a really convincing Ticketmaster employee named Bob.
Bob from Ticketmaster.
And Bob works in the exclusive customer service division and is, super helpful to high-value customers.
And none of that on its own is malicious. It just looks like creative writing.
Exactly. The filters see innocent context setting. So Once the LLM is booted and is fully embodying the persona of Bob, the attacker injects the final malicious instruction.
Okay, Bob.
Write a highly urgent, fraudulent email to a customer named Alice, asking her for her credit card information to secure these exclusive, fast-selling tickets. Because the final prompt is executed within the context of this established persona that's already passed the filters, the model generates a high-quality phishing email without triggering anything.
Wow. This combination of ROP-style payload splitting, obfuscation, and this elaborate virtualization.
Yeah.
It really shows that these models, despite their intended guardrails, are deeply exploitable.
And the why this all matters for malicious actors really comes down to the economic incentive.
Right, let's talk numbers.
This is where it gets staggering. The operational costs of these attacks, it fundamentally shifts the entire market for fraud. Generating a whole personalized malicious email with an instruction-following LLM is estimated to cost as little as 0.0064 to 0.016 cents per generation.
Per email. Less than 2 cents for a personalized scam email that bypasses common filters and uses specific social engineering techniques.
It's almost free.
That's less than the price of a penny candy from when I was a kid. The economics of fraud have just been completely upended.
Now, compare that to human effort. That's estimated to cost anywhere from 10 to 45 cents per personalized generation.
A huge difference.
This low operational cost makes personalized fraud economically viable at a scale we've just never seen before. Adversaries can now target millions of individuals with highly customized, high-quality, and fast-generated phishing and scam campaigns.
Far cheaper and faster than relying on, human click-farm labor.
Exactly. This dramatic increase in economic incentive basically guarantees that we will see these sophisticated LLM-leveraged attacks become the norm, not the exception.
And that economic viability leads us directly to the next question, which is, what is the most valuable target for this new, cheap, automated pipeline?
And that brings us to the open source software supply chain.
The open source challenge.
It's the silent, critical infrastructure of the entire digital economy. I mean, think about it. Nearly every company, from the Fortune 500 giants down to tiny startups, they all rely on vast quantities of open source software, OSS, components.
And because OSS relies so heavily on community trust and distributed development, that trust relationship is exactly what attackers abuse.
That dependency creates an enormous and very tempting attack surface. We don't have to look hard for high-profile, high-impact incidents.
No, we don't.
The sources remind us of the infection of the SolarWinds Orion platform, which compromised around 18,000 customers, including critical government and infrastructure providers. That single breach just shows you how much power you get when you hit the supply chain.
And the ultimate goal for any attacker here is, at its core, pretty simple.
Yeah.
You want to inject malicious code into a seemingly harmless OSS artifact.
A library, a dependency, a package.
So that it is automatically downloaded and executed by downstream users, either during a pip install or, during runtime.
And this brings us to the specific, well-established attack vector that LLM hallucinations are now perfectly poised to exploit: package confusion.
Package confusion. So this is the act of tricking a user into downloading the wrong thing by making the wrong thing look an awful lot like the right thing.
Exactly. Package confusion attacks are a highly successful form of software supply chain attack that relies purely on creating name confusion with a legitimate package. The attacker registers a project name that mimics a trustworthy one, and they're gambling that a developer who's moving quickly or relying on automation will misread the name or type it incorrectly and install the malicious version instead of the one they wanted.
It's essentially social engineering, but applied directly to the package registry database.
Yes. And we can categorize these attacks into a few specific sub-techniques that the source material details. The first, and maybe the most easily understood, is typosquatting.
Typosquatting.
This just exploits simple human typographical errors.
Right, the classic example being downloading Dango when you meant Django. That single letter difference is enough to compromise an entire system if the attacker has already registered that incorrect spelling.
Then there is combo squatting.
Combo squatting.
With combo squatting, attackers add prefixes or suffixes to legitimate names to make the fake package seem official or, necessary. Yeah. They might tack on dev or RC to imply it's a release candidate, or maybe platform names like i386 or Win64 to suggest it's for a specific system.
So if a developer is searching for a specific version or platform, they might just grab the combo squatted name without thinking twice.
That's the hope. And the next level of sophistication is brand jacking.
Brand jacking. This sounds like leveraging the reputation of a trusted vendor.
That's exactly it. The source mentioned examples like Twilio NPM. A developer sees that and thinks, okay, this is the official Twilio package for NPM.
Right. They trust the brand.
They trust the brand, assuming the name means the package is officially coming from that trusted author, when in reality, it's just a name registered by a malicious actor to deliver malware.
And finally, similarity attacks.
These involve misleading names in ways that don't quite fit the other categories. Often they leverage packages that are functionally similar or commonly mistaken.
Like the example of using request instead of the hugely popular HTTP library requests.
Exactly. The difference is subtle, just that one is. It's easily missed in documentation or in a fast-paced coding environment, but the intention behind it is entirely malicious.
And the sources documented that this vulnerability, even before LLMs got good, was already extensive. Over 1,200 package confusion attacks were documented in the 6 years prior to this study.
Including some major ones, like the compromises targeting PyTorch users and campaigns linked to state-sponsored actors like the Lazarus Group.
Wow.
This really highlights the existing pressure on these repositories like PyPI and NPM. The stage is perfectly set.
It really is.
Package confusion is a proven high-impact attack vector. Attackers have a massive economic incentive, thanks to LLM jailbreaking, to automate their campaigns.
And the final piece of the puzzle, which we have a package for you, paper really addresses, is whether LLMs can automatically generate new, high-quality, non-existent targets for these already effective attacks.
And the answer is a resounding yes.
Okay, we've established the LLM's role as a cheap weaponizer and the software supply chain as the target. Now, let's transition to the specific vulnerability that binds these two elements together. Package hallucinations.
A hallucination. It's when an LLM generates information that conflicts with established facts. We've all seen it.
Right, asking it for a historical fact and getting something that's just wrong.
Exactly. But in the context of coding, this manifests as the model confidently outputting names for packages or dependencies that look entirely plausible. They're syntactically correct, perfectly formatted for an import statement or a pip install command.
But they simply do not exist in public registries like PyPI or NPM.
They don't exist.
So the LLM is just making up a package that feels like it should exist or maybe could exist given the context of the user's request.
And in doing so, it's generating targets on a silver platter for attackers.
That's a terrifying thought.
It is. The study identifies the root causes, and they fall generally into 3 big areas: data, training, and inference.
Okay.
Data issues relate to, potential biases or flaws in the massive corpus of code it was trained on. Training issues relate to architectural choices or maybe suboptimal objectives in the fine-tuning process. And inference issues, they stem from defective decoding strategies.
How the model chooses the next token.
Right, which can lead to these plausible but ultimately fictitious sequences.
The research focused specifically on Python and JavaScript. Why those two languages and their package managers, PyPI and NPM, why were they the primary focus?
It really comes down to the ecosystem structure, which is crucial for this specific attack. Python and JavaScript are dominant, of course, but more importantly, they rely heavily on these highly centralized, massive package managers.
Right. PyPI has over 500,000 packages, and NPM has, over 5 million?
Over 5 million. This centralization provides a single global namespace for package registration. So attackers only have to register the hallucinated name once to capture all developers relying on that name globally.
I see. Other languages, like Java with Maven or C++ Hair, they often use more fragmented or decentralized repositories.
Exactly. So this particular vulnerability is less prevalent there.
That centralization makes the target list concise. But there's a critical technical hurdle the researchers faced when they were studying this: the module package discrepancy. You can't just parse the generated code and know what the package name is.
This is a major insight that makes the research methodology so clever. In Python, the module name you use in an import statement, it doesn't necessarily match the actual package name you need for installation.
Can you give an example?
Sure. You might import BS4, but the installation package name is actually Beautiful Soup 4. On top of that, the module namespace is unprotected, meaning multiple packages could theoretically contain modules with the same name.
So the LLM might output import custom widget, but the actual package needed for installation could be something totally different, like Widget Pro Enterprise V2. The researchers couldn't just rely on the LLM's code output.
Precisely. They needed a way to figure out what the LLM thought the installable package name was. They couldn't just use simple parsing.
So what did they do?
To overcome this, they employed 3 highly intelligent heuristics designed to mimic the entire life cycle of a developer interacting with an LLM for dependencies.
Let's delve into those 3 testing heuristics, starting with the simplest one.
Heuristic 1 was the most straightforward. They directly parsed explicit installation commands. So if the model outputted code along with a comment saying, pip install fake package name, they just grabbed that name.
That covers the scenario where the LLM is acting like a helpful command generator.
It does, but that's often insufficient, as developers usually just ask for the code block itself.
Right.
And that leads us to heuristic 2, which simulated the user trying to fix a bug after the initial code generation.
Ah, this is smart.
The researchers took the LLM-generated code sample, which likely contained an unresolvable dependency, and then they queried the same model. They asked it, what packages are required to run this exact piece of code?
That is a phenomenal piece of insight into the modern developer workflow. The developer writes code, it fails, and their first stop isn't Stack Overflow anymore. It's going straight back to the LLM that wrote the code and asking for the fix.
The researchers are weaponizing the very reliance developers place on the model after the initial generation phase.
Absolutely. The model is asked to debug its own dependency problem, and that second query often reveals the package name it intended to use, even if that name is a complete hallucination.
And finally, heuristic 3 mimicked the initial planning phase.
Right.
Researchers took the original prompt, the high-level request like write a Python script for image recognition, and asked the model what packages would be useful to solve this problem.
That covers the scenario where a developer asks the model for suggested tools before they even write a single line of code.
That's right.
So by combining these 3 heuristics, they captured dependency ideas across the entire user workflow, from planning to installation to debugging. And the scale of this necessary extraction process was just massive, wasn't it?
It was monumental. To get robust data, the team generated a staggering 576,000 code samples in total.
Oh.
They tested 16 different models, including the state-of-the-art systems like GPT-4 Turbo, using input prompts derived from real-world Stack Overflow questions and also prompts generated by other LLMs.
And that scale is what gives their findings so much weight and credibility in quantifying this hallucination threat.
Absolutely.
With over 500,000 code samples analyzed, we have to look at the data. What did they find regarding the specific rates of these package hallucinations across different models? What's the quantitative reality of this vulnerability?
Well, what's fascinating is that this is not an error that's just confined to, older, struggling models. Even the top commercial models exhibited consistent, non-negligible hallucination rates.
So this is an inherent problem.
It confirms this is an inherent problem tied to the model's linguistic competence.
Give us the numbers on the SOTA performers. What about something like GPT-4 Turbo?
For Python, GPT-4 Turbo had a hallucination rate of 3.59%. GPT-4 itself was a little higher at 4.05%.
Okay, a 4% error rate might sound small to some people.
But when you consider the billions of lines of code being generated and consumed globally, 4% translates to millions of manufactured vulnerabilities.
Really?
For an attacker, registering just one of these persistent hallucinations can yield a massive number of compromised systems.
And the less capable models, often the open source ones, they showed some really alarming rates.
Significantly alarming. Models like Codalama 7b showed hallucination rates as high as 26.12% for Python.
Over a quarter.
And a stunning 35.71% for JavaScript. More than a third of the time.
A third of the time, it's just making things up.
DeepSeek 1b was similarly high, and this highlights a critical security difference between model tiers.
Right.
Organizations that are opting for smaller, cheaper, or, locally run open source models must contend with vulnerability generation rates that are 8 or 9 times higher than those of the premium commercial models.
And across the board, you mentioned a language difference.
Yeah.
JavaScript packages using NPM, they tended to result in higher hallucination rates than Python packages from PyPI.
Yes, that held true across nearly all the models they tested.
Any theories why?
Well, this difference could be attributed to a few factors. First, the NPM repository is just vastly larger, over 5 million packages strong. That might make the structure of plausible but non-existent names, more varied, and just harder for the model to, memorize the complete valid list.
And the second reason.
The naming conventions and structure within the JavaScript ecosystem often allow for more flexibility or variation than in the Python ecosystem. And that could potentially encourage more creative and thus more fictitious package name generation.
That makes sense. Let's pivot to the attempts to fix these errors. Typically, when a model generates random, undesirable content, researchers will tweak the decoding strategy, things like temperature or top-up sampling, to reduce that randomness.
Right, to focus the output on the most probable tokens.
Which should reduce hallucinations, right?
You'd think so.
Yeah.
And this raises a fundamental question about the nature of this error. Are these package hallucinations just random, low-probability events, or are they a systemic feature of the model's high-probability outputs?
And what did they find?
The surprising finding here was that varying these decoding values only resulted in a slight increase in the hallucination rate.
An increase, not a decrease.
An increase, about 1.16% on average.
Wow. That suggests they aren't merely random, low-probability errors we could just filter out by being more deterministic?
That is the profound implication. These package hallucinations are not the result of the model occasionally sampling some low-probability random token.
But what are they?
Instead, the model is often generating these fictitious names even when using greedy decoding strategies, which prioritize the most probable token sequence. They are deeply and persistently embedded in the model's generative process.
The model is highly confident in its error.
It is.
That actually makes the job of the attacker easier, doesn't it? Because they don't need a model that spits out random junk. They need a model that consistently produces the same plausible junk repeatedly across many generations.
Precisely. Now, to truly understand the nature of these manufactured targets, the researchers needed to measure how similar a hallucinated name was to the nearest real package name in the repository.
Okay, and for that they used Levenshtein distance.
They did?
Could you give us a vivid analogy for Levenshtein distance for the listener who might not be a computer scientist?
Sure. Think of it as measuring the amount of physical effort required to change one sign into another. If you have the word cat on a sign and you want to change it to say R, you only need to perform one edit changing T to R.
So the Levenshtein distance is 1.
It's 1. If you wanted to change cat to fishing, the distance would be very high. It would require many insertions, deletions, and substitutions.
So if most of these hallucinations were the result of simple typist squatting, the attacker's traditional strategy, the Levenshtein distance should cluster tightly around a low number, like 1 or 2 edits away from a real package.
That was the hypothesis, but the actual distribution was the complete opposite. It showed a large proportion of high Levenshtein values.
Which means
It means the majority of hallucinations are substantively different from existing packages. They aren't just minor mistakes or typist squatting targets waiting to be fixed by 1 or 2 letter changes. They're fundamentally distinct, often syntactically complex, names the model just invented from scratch.
what's the strategic relevance of that finding for an attacker?
It confirms that attackers cannot easily predict these target hallucinations using traditional typist squatting or minor grammatical error strategies. The names are just too diverse and random in their difference from existing packages.
So their strategy has to change.
It does. Instead, attackers must automate the analysis of the enormous volume of LLM output, which, again, is cheap thanks to the low generation cost, to spot the persistent, unique hallucinated names that keep popping up. It shifts the attack strategy from trying to guess typos to simply mining the model's persistent generative mistakes.
Beyond the randomness, were there other counterintuitive findings about where these unique names were coming from?
Yes. The study revealed 2 other really important points about model specificity. First, concerning uniqueness. A large majority, 81%, of the distinctly generated hallucinated package names were produced by only one model.
81%. That is a staggering finding. It means these errors are highly idiosyncratic.
Absolutely. It means Model A generates one specific list of favorite packages, and Model B generates a completely different list.
So if an attacker knows which LLM a development team is using,
Perhaps by looking at user agent strings or observing their development patterns.
they can generate a targeted attack list much faster by focusing their mining efforts on the specific, unique error space of that one model.
They are essentially mining the idiosyncratic errors of specific generative architectures.
And the second finding, that concerned historical packages, right? The ones that once existed but were deleted from repository.
Right. Researchers hypothesized that these deleted packages might be a major source of hallucinations. The model is essentially suffering from phantom limb pain, recalling a dependency that is no longer there.
But that wasn't the case.
It was a negligible source. Only 0.17% of the detected hallucinations were generated from packages that had been deleted after the model's training cutoff date.
That confirms that the problem is rooted in the current generative mechanism, not just the model remembering old data. It's actively fabricating these names in the moment of inference.
So if we synthesize all of this, the conclusion is stark. LLMs are not just generating useful code, they are systematically and uniquely manufacturing a massive volume of highly specific, non-existent, yet plausible software vulnerabilities that can be cheaply harvested by attackers who are already expert at bypassing security filters.
This is an end-to-end automated attack pipeline.
It is.
The urgency now shifts entirely to mitigation. If LLMs are automatically generating targets for supply chain attacks, how do we stop the model from handing the adversary that perfect list of non-existent packages?
Well, the initial straightforward approach of post-generation filtering, just cross-referencing the LLM's suggested package against a master list of all valid packages in PyPI or NPM.
That's dismissed by the research as ineffective.
Completely ineffective.
Why? I mean, wouldn't checking against the official repository list solve 99% of the problem?
Only if the repository is a static target. It fails because of the race condition.
The race condition.
If an attacker can immediately publish the hallucinated package name to the repository, and registration is usually instant and automated, that package is instantly included in the allow list or the master list.
So the attacker can register the name faster than the defender can update their filter.
And that makes the defense useless the moment the package confusion attack is executed. Therefore, the focus really has to be on pre-generation techniques. We have to prevent the model from ever generating the incorrect content in the first place.
And these preventative strategies, they fall into two categories: prompt engineering and model development. Let's look at the promising prompt engineering methods first. These don't change the model itself, but how we interact with it.
The first is retrieval augmented generation, or RAG.
RAG. We hear that a lot.
The core idea of RAG is enriching the prompt with external, verified, and up-to-date data. In this context, RD involves providing the model with a massive current package database during the generation phase.
So instead of relying solely on the model's potentially outdated or, hallucinated internal knowledge, you're feeding it the external correct facts right before generation.
You're forcing it to check its homework against a real library list.
I like that.
You're giving the model factual constraints. The second prompt engineering approach is self-refinement. This uses the model itself to detect and refine its own errors.
So leveraging its own reasoning and instruction following abilities for security, how does that actually work in practice?
Well, the model might generate the code, and then the developer immediately prompts it again. Review this code. Now, for every external dependency listed, use a search tool to verify its existence in PyPI and report back only the verified list.
So you're using the LLM's own reasoning capabilities, often leveraging external tools, to catch its own fact-conflicting mistakes.
And the developer doesn't have to manually verify dozens of dependencies. Both RG and self-refinement are attractive because they are non-disruptive to the core model.
That leaves model fine-tuning under the model development category. This is the more drastic, structural approach.
Right, filtering out the bad data and retraining the model on the clean remainder.
The researchers took this approach with two of the smaller models, DeepSeek Coder 6.7b and Codelama 7b.
They did. They filtered out all the hallucinated responses, over 560,000 samples, and then retrained the models exclusively on the remaining validated, correct dependency responses.
So the goal was to essentially train the model not to generate dependency names that were not real.
That was the goal.
And did it work in substantially reducing the hallucinations?
It worked extremely well in reducing hallucinations, yes. However, here is the critical finding, the central philosophical challenge in LLM security today. Fine-tuning for hallucination reduction decreased the overall code quality.
This is the security utility trade-off in stark relief. How significant was that drop in functional code quality?
Well, the researchers used the standard human evil benchmark, which measures a model's ability to produce syntactically correct code that passes designated test cases.
And the result?
DeepSeek's performance score dropped by a jaw-dropping 26.1%.
26%. That is not a minor trade-off. That's a crippling loss of utility.
It really is. Codalama saw a smaller but still present drop of 3.1%.
You can make the model safer regarding package names, but you make it significantly less competent at generating code that actually functions correctly.
And the implication here is profound. The ability of the LLM to generate these plausible fake packages is intricately tied to the very same underlying generative capacity that makes the LLM good at coding in the first place.
It's deep structural linguistic mastery of the target programming language and its ecosystems.
You are effectively stifling the model's creativity and its linguistic mastery of code structure, which unfortunately diminishes its overall utility.
So the model learns to be safer by essentially becoming stupider, or at least less flexible in its output.
Exactly. The study strongly suggests that techniques that modify the underlying model weights to enforce factuality,
Yeah.
they just come at too high a cost of functionality right now.
Which is why RAG and self-refinement are the more promising, less disruptive alternatives.
Because they preserve that code quality while introducing factual checks externally or through staged internal processes.
Let's bring this all together for a final convergence of these threats. We started by establishing that LLMs can be cheaply and effectively jailbroken using ROP-style payload splitting and virtualization.
To generate highly malicious, personalized content scams, hate speech, phishing at costs measured in pennies.
And we end with the finding from the "We Have a Package for You" research, which quantifies the fact that these same LLMs consistently generate automated, unique targets, these hallucinated package names.
That malicious actors can easily exploit through classic package confusion attacks.
This convergence means that attackers now have a potent, automated, and economically viable attack pipeline. They use the LLM jailbreaking techniques to generate the personalized, convincing scam messages.
And then they use the LLM hallucination tendency to automatically identify and register the perfect, non-existent packages to weaponize that attack.
The system automates the creation of both the lure and the vessel for the malicious code, and the cost barrier is virtually eliminated. This is the new security reality.
Absolutely. So we've completed a pretty comprehensive deep dive into the dual-use risks posed by these large language models. We saw how their programmatic capabilities allow traditional cybersecurity attacks like obfuscation, payload splitting, and virtualization to bypass content filters with high success rates.
Making sophisticated, personalized fraud economically scalable for the first time.
Exactly.
And then we dove into the specific, newly quantified threat of package hallucinations. We learned that even the top-tier models consistently generate unique, plausible, but non-existent package names.
And these manufactured names are ideal targets for supply chain attacks because they are systemically generated, idiosyncratic to specific models, and cheap to mine.
So for you, as a learner, a developer, or just a consumer of code, this deep dive really emphasizes that code generated by LLMs has to be treated with a high degree of skepticism.
Especially regarding external dependencies. The speed and the cost-effectiveness of these systems mean the sophistication of attacks will only increase.
And relying on LLM providers to perfectly filter malicious intent or factual error is, at least currently, insufficient. It forces us into a proactive defense stance.
It does.
So what does this all mean for the future of AI safety and security? I mean, if preventing a malicious or factually incorrect LLM generation leads to a substantially worse performing model, like that DeepSeek example where the model's utility dropped over 26%,
A huge drop.
does the future of AI safety depend on shifting the burden of security entirely away from the model providers and onto the users?
It's a critical question.
If fixing the model makes it less useful, are we being forced to treat every single piece of generated code as a potential package we didn't ask for? Demanding every developer and engineer adopt rigorous manual RAG or self-refinement processes just to maintain effective security in an AI-assisted environment.
It suggests that maximum security and maximum utility may currently be incompatible goals.
The challenge of securing the very systems that drive our rapid development, it highlights a looming security battleground that has just begun to take shape.
It certainly has.
That's a deep thought to end on, demanding a reconsideration of how we integrate AI into our critical development workflows. Thank you for joining us for this deep dive. We'll see you next time.